Well, it's a great pleasure to listen to Luis Garcia Larrea, who's going to be talking to us about pain and the perception of pain, something which is in front of us all. And what about if pain is a distributed system? What about if it's just like vision and audition and what have you, and it's actually distributed across many regions of the brain? And what kind of a consequence would that have for our future in understanding pain? Luis, it's up to you.
Donc, merci beaucoup de cette invitation. Comme ma langue maternelle n'est pas le français, je sais que vous parlez français, mais comme ma langue maternelle n'est pas le français, I continue in English, if you don't mind. Okay, thank you. So I will be speaking about pain, and I put this kind of, so to say, attractive title to make you come. As you know, in the unit, in the team, we are dealing with several aspects of pain, and today we just speak about this first one. We are also dealing with abnormal pain, with neuropathic pain, diagnosis and prognosis, etc., and with therapeutics for pain, especially with cortical neurostimulation. So we will stick to physiology today. And to stick to physiology, we need to start with something that's called the pain matrix. Some of you know probably what this means, and its trials and tribulations. The pain matrix starts from the search of the neural basis of consciousness, of self, the substratum of the physical self. He considered was a network of neurons extending throughout the brain, and he stated in a very nice paper in Teens that the neuromatrix for the physical self indeed generates the neurosignature pattern for pain. Now, this at that time was a definite conceptual advance because, believe it or not, during more than half the last century, it was considered that pain was integrated in the thalamus, no cortex at all. And when, after the 50s, we started to consider, mainly because of clinicians that saw patients with cortical lesions and pain, that the cortex could have something to see with pain, it was considered as a kind of a sequential thing. First, pain sensation, and then reactions that were cognitive and emotional. So the idea of Melsack, considering that the different components of pain were processed in parallel, the cognitive, the emotional, the sensory, and that there was no such thing as a pain center was definitely a novelty. And this novelty was very rapidly endorsed by functional imaging studies in '91. There were two papers, one from London, the other from Montreal, showing that there was multiple representation of pain. What means multiple representations? Well, it means something like that. Is if you get from 35 degrees centigrade to 50 degrees, so after 48 probably you feel something like pain. What you see is not a big spot that becomes bigger and bigger. What you see is a network, or at least a series of regions, that is what we call the pain matrix, that become progressively disseminated and progressively bilateralized. This is a very robust result. There have been dozens of papers showing this kind of image, which is very much reproducible. But of course, very soon, it became clear that most of the regions that were included in this matrix were not totally specific for pain. But we have inside, we have modules for sensory processing, other regions that speak rather from of attention on orienting, regions that could support the transfer into vegetative reactions, and regions that could be in charge of some cognitive control. So this was clear almost since the beginning, and yet there are so much confidence in functional imaging that since a number of years now, there is many studies that consider that just observing a pattern of brain activity similar to the pain matrix can be considered as an objective evidence that an individual is suffering pain physically. which in my opinion is a big error, but you can find patients, papers like this one, published in relatively good journals, speaking about social rejection, social exclusion, and consider that since there is an activation in the anterior cingulate and in the anterior insula, in the anterolateral frontal cortex, which are very prominent parts of the pain matrix, so the experience of and regulation of social and physical pain share a neuroanatomical basis. And this is relatively small. Other papers are appearing now that is explaining you that you physically feel pain when your girlfriend is getting with someone that is not you. So in reaction to this, there has been a bit the opposite side. And the opposite side is trying to demonstrate that nothing in the pain matrix is specific for pain. Using kind of these type of images, if you try to tell me rapidly which of these sets of images corresponds to a nociceptive stimulus, which to a non-nociceptive, which to an auditory, which to a visual, is quite complicated. It's not impossible, it's not easy. Here the response. It is very difficult to differentiate a noxious and an innocuous somatosensory, and even from an auditory. So there is a move now, considering that what we observe and we call the pain matrix is just a salience detection system for the body. So it's considered that, in fact, this is just a salience detection system, a mechanism which will fire up when something which is important for the body integrity is detected, whatever the sensory channel. So this is the point, is whatever the sensory channel. This might be true, but in general, we don't do not mistake a heartache for a toothache, which means that something specific for pain, for nociception, should exist within this pain matrix. And what we shall be dealing today is whether we can develop models that allow putting together and explaining how a sensation which is well defined for us, we know that it is bodily pain, can be subserved by networks that are in the main quite specific. So we should start by nociception in the beginning. What criteria should we consider to say that the cortical region is a nociceptive region? Well, I have put here 4 plus 1. It should be anatomically plausible. It means that it should correspond to anatomical targets of the spinothalamic system, which is the one which is conveying the pain and temperature signals. It should be, this region, it should be activated by noxious stimuli. If we give an noxious stimuli, we should get an activation obligatorily. We should be able to trigger pain if we stimulate this region, if it's a sensory region. And we should abolish pain or lessen pain if you do a lesion in this region. And then for those of you who are involved in pain, we know that chronic lesions in any part of the pain systems are able to generate chronic pain. So they will be the 5. So in part in the team, we have contributed to try to persuade you that each and every one of these requirements is fulfilled by a particular region which is situated in the posterior granular insula and its adjacent operculum. First, anatomical plausibility is plausible. Which are the cortical targets of the spinothalamic system in primates? This has been showed very nicely using anterograde transport of herpes virus from spinothalamic neurons injected in the dorsal horn and then transferred to the thalamus and from the thalamus to cortex. So the system, you know it very well. You inject here, the virus is taken up by the neurons and then transported and then infect the second order neurons, and then it goes to the cortex and is going to infect the third order neurons there. This allows to map the thalamic targets, which were already relatively well known, but what was very much less known were the cortical targets. And when you see the cortical targets, 30 plus 40, you have 70% of the spinothalamic targets that go to the opercular insular cortex. So either to the posterior insula, to the granular insula, or to the adjacent operculum near S2, but not exactly in S2. Then you have almost 25% that goes to the motor cingulate, not to the anterior cingulate, to the motor cingulate, the mid-cingulate part, and the rest, 5 to 6%, distributed in primary somatosensory and motor areas. So we have a very, very big projection of the spinothalamic system to the opercular insular cortex. And when we came to human beings and we tried to receive responses to purely nociceptive stimulation, we can do it with a laser. A laser stimulates selectively the A delta and C fibers, so just nociceptive ascending system. Then the regions that we record with an EEG and source reconstructions are indeed in this posterior part of the opercular insular region and in the mid-cingulate. You may say this is mathematics, this is source reconstruction from the scalp EEG, but when we come into the brain and we put the electrodes in the brain, we discover that responses which are locally determined here in the opercular insular region and appear where this thing had predicted. So in the posterior insula and operculum and in the mid-cingulate. Look at an electrode here in the perigenial cingulate does not record a consistent response, but an electrode here in the mid-cingulate does record a nociceptive response. So we have the first point, which is we need to have responses there. The second point, if you stimulate there, do you get pain? And the response is against yes. And this is the only cortical region where electrical stimulation has been shown to induce acute pain. This is a work essentially from Laure Mazzola, Jean Isnard in the epilepsy department of François Mauguière, dealing with epileptic patients. All these white dots are dots of stimulations where patients have been stimulated for clinical purposes, and these, I don't know whether you see the red dots inside, these are the only points where it was possible to evoke a painful sensation, acute painful sensation. Now in this last paper from 2012, Laure Mazzola and Jean and Roland Perron and François Mauguière have reviewed up to almost 5,000 stimulation in the brain from all parts of the brain. And again, the only region where you can induce acute pain is stimulated in the posterior insula and medial operculum. You can stimulate, you can also get stimulation spontaneous. This is a patient with a posterior insular lesion here. And this lesion is able to produce spontaneous seizures. This is the seizure recorded with an electrode which is implanted without the lesion. This seizure characterized exclusively by pain. So if I can put this stack, look at this guy. The only thing that is being here, he's suffering. He's not losing consciousness. He's able to respond to everything. He's just suffering during this session. Okay. This is the only manifestation. So we can induce pain there. And this is the same seizure, but now seen from many other electrodes. No more pointer. Yes. No more. So you see the spike. The seizure starts there. If I had another thing I could point with this. Okay. No. Okay. Okay. Bon, c'est pas grave. Okay, the point there is that from this point where the posterior insula is triggering the seizure, it can also trigger the rest of the pain matrix, at least the rest of the part of the pain matrix where there were electrodes to record in about 80 milliseconds. So in 80 milliseconds, you had activation of the mid-cingulate gyrus, the mid and the anterior insula, and the parietal operculum. So it's like a funnel from the posterior insula that you go to the rest of the pain matrix. Now we come to the lesions. This region is the only one where a lesion is able to temper or make disappear the pain perception. You see in the right part a very nice, let's say, nice lesion of the anterior insula. This big lesion of the anterior insula does not create a pain deficit. The lesion in the posterior insula and in the left, yes, it does create a pain deficit. And if we come to electrophysiology, this very small lesion in the posterior insula is able to selectively abolish the cortical responses to a laser stimulus and the vegetative responses to a laser stimulus, which is selectively nociceptive, while leaving intact the responses to a non-nociceptive electrical stimulus. So we can dissociate perfectly just because of this small lesion. So I hope to have persuaded you that we have something that reminds a sensory set of targets for nociception that are activated by noxious stimuli, that can trigger pain if stimulated, that can trigger painful seizures, that can activate other components of the pain matrix, that can generate a loss of pain and temperature while preserving lemniscal modalities and inducing chronic neuropathic pain. This I did not show you, but believe me, please, because this is true. So what I propose is to start here and to call this not a pain matrix, but just a nociceptive matrix. Okay? This is not yet pain, it's just nociception, cortical nociception. Pain is a conscious sensation. So going from nociception to pain needs some other things. It's like going from a text to context. And obviously, the pain matrix, as we know it, comports many other regions out of this nociceptive network of the posterior insula and the mid-cingulate. So we have essentially these four other regions which are very much consistently activated. The mid and anterior insula bilaterally, the anterior cingulate, the dorsolateral prefrontal, and the posterior parietal region. These are almost more than 90% of the cases present in the pain matrix, and with a bit less incident we have others. So the characteristics of these other regions, which are shall call the second order matrix, is like a mirror image of the nociceptive matrix. First, none of these regions are a direct spinothalamic target. None of these receive spinothalamic projections. None of these regions can evoke pain if you stimulate them. Destructions of these regions of the pain matrix never induce hypalgesia. And most important, all these regions are also activated in context that does not involve pain. And they are extremely contextual. It means that their contribution vary depending on the context where the noxious stimuli are applied. So what would be the functional, the function that they subserve? Well, they subserve, first, the translation of sensory responses into vegetative reactions. And this will be the thing done by the insula. They sustain cognitive and evaluative processes. They can modify the sensory gain by top-down influences on the nociceptive matrix. And most importantly, they ensure conscious perception. Because the nociceptive matrix, the posterior insula, medial operculum, cingulate, cannot sustain by itself the conscious declarative perception. We know that sensory areas by themselves are not able to sustain this. And in the case of pain, we have some direct evidence. For example, the nociceptive matrix, the mid-cingulate, insula, operculum remains active during sleep, which is obviously a state of not consciousness, and remains active also. This is the work of Hélène Bastugy in epileptic patients too. And the works of Kasubek shows that the nociceptive matrix, the posterior insula, S1 here too, the mid-cingulate, the two posterior insula, are also active in patients in vegetative state and even in some patients in coma. While they awaken, we start to see activity. This is, of course, to nociceptive stimuli. We start to see activities in prefrontal and parietal powers. So the second order matrix is also ensuring that there is some conscious perception. So we pass from nociception to real pain. To have conscious perception, you need this and this. And for those of you who are interested in this type of conscious network, go to the works of Stanislas Dehaene and Lionel Nakache who have worked much on this similar type of network, but with visual stimuli. And these two regions are essential to ensure that the subject will be able later to consciously declare that he has been stimulated. So, first stop, without the nociceptive matrix, the bodily specific character of the pain perception is lost. We need to enter by this nociceptive matrix if we want to recognize the pain as being from the body. But without the second order matrix, nociception is not translated into pain. I mean, we don't have conscious perception, and we don't have all the contextual things like amplification by attention or vegetative reactions or other concomitants. This second order matrix is extremely sensitive to context. I told you this is one example, even if it's a bit old, a work that we did with Roland Perron some years ago. But this is just to show that the simple fact of putting your attention in the body territory that is being stimulated increases enormously the regions that you activate by the same stimulus as compared with a distraction. And we compare. When you compare the regions that are interested in intensity coding, that is comparing just all the responses, attentional or distractive, to high stimuli, with all the responses to low thermal stimuli, you get a very small network. But when you compare the responses to stimuli that are attended, selectively attended, with the stimuli that are not attended, then you get a very, very important network. And if you put these two networks together, you reconstruct almost the pain matrix. So this region, this second matrix is very much sensible to the context. So what if we try to isolate the context, to strip away the nociceptive matrix, and to get only the second order non-specific matrix? This is interesting because the first team which showed this kind of data was about almost 10 years ago, like Tanya Singer, making experiments, doing experiments on pain empathy for pain. When you compare the brain responses during the real, actual perception of pain and the responses when the subject is just figuring out that her loved one is also suffering in another room, just this imagination of the pain of someone you love, and you compare the two kinds of responses, you have a series of regions where there are a convergence between the two. And this convergence is essentially in the bilateral anterior insula and in the anterior cingulate. So this does not pertain to the nociceptive matrix. This pertains to the second order matrix. And Tanya Singer underlined this, saying that the empathic experience does not involve activation of the entire biometrics. This co-activation of the two anterior insula and the anterior cingulate is a very robust result in empathy for pain. So you know, no doubt, this kind of slides from Jean de Setti and Jackson. And you know that when you compare the responses to this kind of image and this kind of image, you get a difference, and this difference is essentially in the anterior insula and the anterior cingulate, just in single. But not only for this, just seeing faces in pain also activates the anterior insula and the anterior cingulate. Even in patients who cannot feel pain, the patients with a congenital insensitivity to pain, they do not know what is pain. But even in those patients, seeing these kind of figures activate the anterior insula and the anterior cingulate. This is a very, very robust. And it's very contextual. Because if you dislike the person you are seeing in pain, these responses are going to be tempered. And this was also showed by Tanya Singer, just making you play a video game with someone who was cheating to you before you saw him suffering. Okay. Immediately, would you compare the anterior insular responses when you see the fair player or you see the unfair player suffering, you see that if you are a woman, they decrease. If you are a man, they disappear. Okay. So this is contextual. These responses are contextual. Now, plenty of people consider that they are pain-related, that they appear when you are seeing people in pain. Well, they are no specific for the observation of pain. Perceiving disgust in others activate the anterior insula. There are plenty of cases of this, and this is a very nice study which was done by someone that we know, no doubt, but simply observing this face of disgust activates the anterior insula. But if someone makes you feel guilty, just with a script, and you feel guilty, and by feeling guilty, activates your anterior insula and your anterior cingulate. Always this triangle. So, Wicker, 10 years ago, suggested that there was perhaps a role for the anterior insula in transforming unpleasant sensory input into vegetative reactions and the feeling of disgust. This is sensible. This is sensible, and it's supported by some observation done in our hospital by Pierre Colac, who remarked that when the ventral insula was stimulated, so the anterior insula was directly stimulated, the patient never felt pain, like with the posterior insula, but tend to say things like this: it's not painful, but it's really difficult to stand. It is really unpleasant. But unfortunately, you don't need just unpleasant stimuli to activate your anterior insula. Here you just detect targets that loom or that recede, and you activate your anterior insula and your anterior cingulate. And the stimuli needs not to be unpleasant. This is a stimulus that could be unpleasant for most of you, especially when you see the following. Okay. But this has been proposed also to sadists who are in jail, serving jail because they have done this and they take some pleasure in doing this. And when you compare the responses to these kind of videos in sadist and non-sadist, well, the responses are rather the same. So you don't need to see something disgusting. You don't need to see pain to activate your anterior insula. So if we start from what was said before, a role for the insula in transforming unpleasant input into vegetative reaction and a feeling of disgust, perhaps we should change this. The anterior insula has a role in transforming behavioral relevant input, whatever, into vegetative reactions and the feeling that one gets. It might be pleasant or not. So, two networks. One that I called an nociceptive matrix, which is specific for sensory coding, for orienting and withdrawal. This is the motor cingulate. And then a second order matrix, which is non-pain specific, but ensures consciousness, ensures amplification or limitation of the pain you get, cognitive control, vegetative reactions via the anterior insula, and the immediate perception that you get. The two get what we call the pain matrix. The second order matrix is able to influence the first, at least in two ways. There is, of course, a top-down modification of sensory gain. There was an animation here from a Mod 4 that I lost, but when you are recorded in the posterior insula and you ask a patient to pay attention to the pain or to just read a book, you see immediately that the attention that you get makes that the response of the posterior insula, so the nociceptive network, increases or decreases, which means that this second order matrix is influencing the first. But the influence can also be downstairs, because the vegetative reactions that you get here are going to make you move your guts, for example, or contract your stomach. And via the splanchnic nerves, you are going to send spinothalamic inputs to the nociceptive matrix, which may finish the end. So we have not just two networks, but two intermingled networks. And fortunately, the pain experience has been shown that to be changed in some particular context without involving any change in the two matrices that we just described. It is that it would be too nice to have just two bottles in the brain. But there are a number of experiments, relatively recent, that show that you can dramatically change what you report of your pain, and then when we look at the pain matrix has not changed at all. Now, these types of experiments make me think that there is perhaps a third round here, another level of modulation. This kind of experiments involved a bit more sophisticated settings. We have, for the moment, observed what was feeling pain, or observing, either observing pain or observing things that may activate another matrix. Now, we can see what happens when you feel pain while you are observing pain. It's a bit more complicated. The typical setting could be like this. It is you try to put your subject into micro-emotional states, including those of observing pain, but not all. That may, with pictures or with videos, we see things like this, things like this, things like this, and you put in between electrical shocks or thermal stimuli, something that can be painful or not painful. So you mix the painful stimulus with the visual context. And then you have, of course, the psychophysical, the subjective reports, and then physiological markers. You can do it with fMRI or with high density. And this is the work that was done with Fabio Godinho recently. These are the kinds of things you see. These are images that can be pleasant or unpleasant. This is very much unpleasant, for example, for anything. This is pleasant for everybody. This is very light. This is pleasant for everybody too. And it tends to be highly unpleasant also for everybody. You see that I put men and women because we try to separate, because the classification of what is pleasant and unpleasant is not exactly the same in men and women. So when you receive painful shocks, which are of the steady intensity. You don't change the intensity of the shocks, of course. But when you receive these shocks, while seeing images highly unpleasant, you tend to rate this shock as higher in intensity than when you see pleasant or neutral images, without any difference between neutral and pleasant, by the way. Well, this, at the time, the first time we demonstrated, it was new, but it was highly expected. Okay, we call it compassional hyperalgesia. What it was a bit less expected and more interesting, in my view, is that once you have matched for unpleasantness, this effect was specific to images that show human pain. That is that this change in the quotation of the pain change when you saw images like this one and not when you see images like this one, while all these images are equally unpleasant. But there is a very big difference. These images speaks of your body or the body of someone. So there is some specificity. But if we get to the point, you can observe this effect can arrive even when you see things which are not very painful, like this one. You perhaps recognize because they are actors, they are not real suffering. So just seeing these kind of images can increase your own pain when you are looking. But when you look at the pain matrix does not change during this manipulation. And when you look at the electrophysiological responses, when you compare this response when the subjects say 4 in 10 and this 7 on 10, so a very big difference in the subjective rating, the difference is really tiny, and it happens very late in on electrophysiological grounds. Starting at 350 milliseconds is really very, very late doing this. It was so weird that we tried to reproduce it with fMRI, and the results are quite the same. When you suffer because you are seeing someone in pain and then you have pain at the same time, the regions in green that constitute what we call the compassional hyperalgesia network, so the regions that co-vary with your sensation, are quite distinct from the red regions, which are the regions of your pain matrix. So there are very, very little overlap. And these regions in green tend to concentrate on very high order regions in the brain, prefrontal regions, ventrolateral, very anterior, or ventromedial, orbitofrontal, perigenual cingulate, and sometimes too in the carrefour, in the parieto-occipital. Before trying to explain this, simply trying to show you that this has been reproduced with other methodology. This is a nice paper from Vic et al. In Oxford, but she did it with Polish people because she wanted to have very faithful and very Catholic believers and practicing people, because the methodology consisted in trying to modulate the pain they receive by either looking to a sacred image of the Virgin Mary or to a profane image like this. And the psychophysical result was that pain was modulated by this kind of images exclusively in believers, in Catholic believers. And when she looked to the regions that were covaried with these changes in the subjective ratings, well, again, was nothing in the pain matrix. It was just in the ventrolateral prefrontal, and perhaps something that could be called the ventral tegmental area. There are at least 4 or 5 recent examples of this. I show this one because it's quite nice and well done in Montreal in the group of Pierre Anville, studying Zen meditators. And again, Zen meditators, well, they received pain. they can modulate their subjective pain, and when they modulate the subjective pain by meditation, while they activate these areas in blue. And surprisingly, they are able to decrease their perception of pain, while the activity in the pain matrix in red is indeed increased. So this is the more nicely decoupling I've ever seen. So your experience is low pain, your pain matrix on the basis increases in activity, and there is another network which is essentially prefrontal and perigenual, which is active at the same time. So I think that we need definitely another of an emotional modulation, of a kind of reassessment that is going to produce a delayed perception and a kind of memory encoding, which I call the subtext. I call this a subtext because you know, probably if you are familiar with the actor's jargon, that the subtext is essentially what is going underneath the text. When you tell something, okay, are you all right, ça va? Oui, ça va, okay? This is subtext, ça va pas du tout. But you are saying something. That this consideration that things don't match up and that something is going on underneath the words in opposition to the words is a bit what this third order matrix, subtextual matrix, is doing. So this is the whole model now. When you apply a noxious stimulus, you have a first activity, very, very rapid in 150 to 300 milliseconds, which is responsible for sensory encoding, withdrawal, orienting, essentially in the posterior insula and cingulate, also, of course, a bit the thalamus. This is the nociceptive matrix. This cannot ensure conscious, declarative perception of pain. For this, you need a contextual matrix, which is modulated by attention, by anticipation, which is responsible for vegetative reactions, and which provides the immediate conscious percepts, like in kinetic models. You have some interaction between the two. Of course, this is triggered by this one, but this can also modify this one. And then you have, at the following, another one, which is able to change the percept by a kind of subtext, which needs higher order level, which is not in the pain matrix, which does not appear in basic experiments of pain, when you just go and take your subject and make a nociceptive stimulus and try to get the pain matrix. You never obtain this one because there is no reason to change anything. But in ecological conditions, you can obtain this. And the convolution of this gives you the pain memories. From a practical point of view, the fact that you get the pain memories there and that you have this possibility is extremely important, because it means that you can modulate the pain of your patients, not only going to the nociceptive matrix and giving opiates and giving paracetamol. You can also modulate the appraisal of your patient's pain by playing at very, very high level, which is, in my view, very much important, because, in fact, I lost, excuse me, this is important, because the last slide is this one. Okay. This is important because pain memories are what we get, and this is in Spanish, but I can translate. Life is not what you live, is what you remember, and pain is life. So if you remember your pain, this pain becomes true. So this is very important, and this is the real last slide. Thank you very much.
You didn't talk about pleasure, and doesn't it always come along with pain? I thought you was going to touch on it when you talk about the sadistic. I suppose that comes into your third matrix.
Okay. Pleasure is the other side of the coin, but plenty of these, especially the third order matrix, is involved in pleasure experiments too, especially the ventral tegmental area, for example, and the anterior striatum. And in fact, there are now about 5 or 6 experiments having demonstrated these changes in the pain perception without moving the pain matrix. And half of them are tapering down pain and the other increasing. But the network that you get is essentially the same. So in one case, you are indeed tapering pain, so going through to pleasure. Right?
No, but for Sard, pain was an essential aspect of pleasure. No pain, no pleasure. No pleasure, no pain.
No brain, no pain, neither. But yes, if what you mean is that we live of contrast, and if you cannot compare a situation with another, this situation has no sense, then I agree. Yet, there is also a kind of neutrality, like you have affective neutrality, you can have a sensory neutrality, what they call our ancestor le silence des organes. And this is neither pleasure nor pain. If you take pleasure of this, this is an intellectual pleasure, but not physical pleasure. So I think that between the physical pleasure and physical pain, there is a very important subjective difference. And one of the challenges in the next 10 years is to understand why the underlying circuits seem to be the same. And this, I do not think that functional imaging can get the response.
Angela.
First of all, thank you for this very interesting talk. And my question concerns frontal limb pain.
A bit louder, please. I'm getting deaf.
My question concerns frontal limb pain. Okay, can you hear?
Phantom limb.
Phantom limb
pain.
Phantom limb pain. Okay.
Yeah, and I want to know, where do you put phantom limb in your 3-stage model? Okay, or pain matrix, because this is a type of pain that mimics nociceptive. I mean, I would put in a nociceptive stage, but I mean, it's a pain that where the body part is not there. So,
this is a very good question. When you have phantom limb pain, you have your spinothalamic system, which is intact. What you have lost is the input to the spinothalamic system. So I believe that phantom limb is a kind of combination of excessive or distorted spinothalamic input, which has been demonstrated in amputated animals, and cortical reorganization that you have shown nicely in Ertafleur, etc. I do believe that the distorted input from the spinothalamic and the organization in the thalamus is relevant for this pain. I'm not completely sure that the cortical reorganization that we see is directly relevant for the pain, because for the time being we only have correlational models. So we know that these patients have, for example, a shrinking of the amputated representation, and at the same time that you can cure pain, you can get the representation enhanced. Okay, we have done it in normal subjects and it works, but this is just correlational, and sometimes you get nice uncorrelations. That is a patient that has a very small modulation or shrinking, but a very big pain, and the opposite. So I think that there is something in between, and that this reformatting of cortical representation are real, but perhaps they are not directly related to the pain, at least in the sensory motor cortex. Among other things, because you saw that the sensory motor cortex is receiving perhaps 5% of the spinothalamic input. Let's say that it is 10%, okay, but it is a minimal as compared what is receiving the posterior insula. So if we had the means, it would be perhaps important to go to the posterior insula and to look to cortical reorganization by differentiation there.
Any more questions?
Yes.
Down here in the front. I just wanted to ask you, is there really any real memory of pain? I thought women only had a child more than once because they couldn't remember the total agony of having the child the first time.
You have nice memories of pain, and even experimentally, for example, there's the group of Fred Lenz in Baltimore has reproduced angina pectoris in Parkinsonian patients who were being operated upon in the thalamus. And while the electrode was passing and they were testing by stimulation in stimulating the posterior nuclear group in the posterior part of the VPL, not really in the VPL, it was able to reproduce the exact pain that he had endured. And there are other cases where there is one case of a woman who had the labor pain reproduced in the operating theater. So you can, in general, when it is experimentally done, it's by stimulating the thalamus. And in general, the posterior thalamus, the supragenicular posterior complex.
But that's by some sort of stimulation of the brain.
Stimulation.
But can a person actually really have a pain imagery as such? Do people actually have, can they really imagine what acute toothache is like? I can't.
In most normal subjects, I feel it is impossible, a bit like it is quite impossible for most of us to have a real memory of the taste of wine, for example. You cannot figure out, you can figure out the 14th Symphony of Mozart easily, but try to figure out the Gros Hermitage that you took 1 week ago. This is quite not the same. So I think that is related to the type of cortex that is encoding this, which is not really the same. The nociceptive matrix, is not, has not the same capabilities of contacting memory and of formatting memories as other may have.
Last question.
I'm not sure you talked about it, so I just want to ask again. So, is there the involvement of the somatosensory cortex in that second or third pain matrix? Because I was very surprised. You mentioned it, but you didn't quite answer it, or I don't know if you did, or I missed it. But we do know where the pain comes from. And so is there any clear answer about that?
In any case, it does not come from the primary somatosensory cortex. The primary somatosensory cortex is not able to generate pain if you stimulate it directly. It belongs to the nociceptive matrix because there are perhaps 5 to 10% of spinothalamic axons that go to the S1, and there is a nice paper from Modfo, it must be there, in human brain mapping just this year, showing that you can, in fact, record directly responses in S1 and M1 to a laser stimulus. So there are nociceptive neurons there. But when you do a lesion in S1, you don't get pain anesthesia. When you stimulate S1, you don't get pain. When you look at the projections, there are very few projections, so we cannot consider S1 as a pain receiving or main pain receiving system. So pain is not generated in one place in the brain thing. This is the point. Pain is a network, and this network is able to regenerate itself. So don't look for a pain center. There is no such thing as a pain center.
No, it's not what I mean, but let's take it the other way. If we completely remove the somatosensory cortex, can we know where the pain comes from?
Yes.
Well, on that definitive answer, we close for the evening. Thank you.